So today we're going to start talking about mixtures. There's two types of mixtures that we're going to talk about. Can anyone name those right off the bat? Yeah, Isabel, what do you think?
Homogeneous and heterogeneous.
Perfect. Okay, homogeneous and heterogeneous. Okay, but the mixture in of itself, okay, a mixture in its most general sense is a blend of two or more types of matter, each which retains its own properties and its own identity. Okay, so we're not becoming something new. We're just blending two things together. They each retain their own identities. Okay. Most mixtures are able to be separated again. Okay, they can be separated once they're mixed. Whenever we have a mixture and we want to have a proper mixture, we need to state the quantities or the composition of the mixture. Okay, we like to state the composition. So it's 30% salt, 70% water. Okay, or things like that. We want to state how much of each of those particular components is in this mixture. We can do that a couple different ways, but the most simplest way is just by percents. Okay, it's this many percent of this compound and this percent of this compound. Okay, so here's our example of stating our composition. Okay, a percentage is our easiest way to do that. All right, so let's look at what a homogeneous mixture is, or homogeneous. These are ones that are uniform in composition. Okay, what's it mean if something is uniform? Yeah, good. It's the same throughout. Okay, so a homogeneous mixture is the same throughout its entire mixture. Okay, everything is spaced evenly. Everything has the same concentration throughout the entire thing. It's not like things have settled to the bottom or anything like that. Everything's the same throughout. Same proportion of components. It's not more concentrated at the bottom. It's not more concentrated at the top. It's the same throughout the entire thing. Okay? These homogeneous or homogeneous mixtures are also called solutions. So a solution is a mixture that is uniform throughout. Okay? It's the same throughout the entire thing. Okay, so a heterogeneous mixture, what do we think that might mean then? Not the same, okay? A heterogeneous mixture is something that is not the same or not uniform throughout. It can be separated easily or by certain everyday means. Okay, we might be able to filter out a heterogeneous mixture. We might be able to pick it apart with our fingers depending on how big the pieces are. We can easily define the components of a heterogeneous mixture. Okay? If we want to separate a mixture, they can be separated by these means: filtration, centrifuge, or evaporation, among other things. Okay? You can use magnets to help separate things out. You can filter like we talked about. A centrifuge is where you spin it really, 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 really fast, and the solid parts begin to fall out of the bottom. Okay? What's evaporation mean? Yeah, Braden, what do you think?
The liquid turning into a gas.
Yeah, liquid turns into gas. So our liquid or would start to dissolve, I guess, evaporate off the top. Okay? Very good. So, a homogeneous mixture is the same throughout. Okay? Everything looks the same. There's no chunks in it. Everything should be mixed properly so that it's completely the same throughout. A heterogeneous mixture can be picked apart. Okay? We can easily separate it out. Okay? So what I want you to do with your partner now is, again, think of 3 heterogeneous, 3 homogeneous mixtures. Okay? In everyday life. A pure substance is different than a mixture. Okay? A pure substance has a fixed composition. Okay? It has a fixed composition, and it's different from a mixture. Okay? A pure substance has a very exact composition. That means it's made up of the same exact thing every single time. And every single sample you take of that pure substance looks, acts, behaves the same way. Okay? You wouldn't get an extra concentrated part of it or anything like that. Every single section of that pure substance looks the same, acts the same, has the same properties, same identity, things like that. Okay? So a pure substance has a fixed composition. You don't have, we wouldn't consider salt water a pure substance, right? We can make lots of different concentrations of salt water. We could have 90% salt and 10% water, or 90% water, 10% salt. Okay, all of those things are mixed compositions. We want a fixed composition. So we want something that looks the same, acts the same, is the same every single time. Okay? So our fixed composition or our pure substance is so clean and so exact that it can be used to identify the substance. Okay? Those particular properties can be used to identify the substance. Okay, whereas in a mixture, you would look at the properties of the mixture depending on the amounts in that particular mixture. Okay? Pure substance have fixed compositions. Fixed compositions. I want you to remember that. Okay? Mixtures, and on the other hand, have different amounts of compositions or different compositions that could be made. Okay, so we want to make sure that we understand the difference between those two. All right, that's what we mean by composition. It's made up of the same components. Okay, so for example, water is a pure substance. Water always contains 11.2% hydrogen and 88.8% oxygen. If you look at its mass, water always contains 1 oxygen and 2 hydrogen molecules, okay, H2O. No matter what water you look at, it's always going to have those particular properties. Okay? So water is considered a pure substance. Okay, pure substances can be either compounds or they can be elements. Either one. Okay, as long as it has a fixed composition. Okay, so there's the examples underneath of those. Water would be considered a pure compound. Sodium or copper or zinc or chloride or whatever element you want to look at would be considered a pure element. Okay? And what makes it a compound? Do you remember? Alright, so we're going to first start basically where the periodic table started. Okay? The periodic table started with only 60 elements. Okay, so in the mid-1800s, when this first periodic table was formed, there was only 60 elements to be put into the table. Okay? Today there are many more than that. Okay? A scientist by the name of Mendeleev Have you heard that name before? Mendeleev? Good. Okay. He developed some organizational system for the elements. Okay. He was the one that first put them together in what we consider the periodic table. His table looked a lot different than the one that stands today, but he began organizing them. Okay, and kind of gave us a system as to how these things could start to be organized. Okay, his first organizational system was in order of increasing atomic mass. Okay, he put them in order of atomic mass. Then he grouped them by ones that he thought behaved similarly. Okay. And both of those trends are still intact today. Okay? The periodic table today is not organized by atomic mass. It's organized by atomic number. But mass generally increases with the number. Okay? So we're going to look at that more in depth here in just a second. But he was on the right track. Okay? And he grouped them by things that he considered to behave similarly. So this guy grouped the elements that had been discovered, okay, by their atomic mass and by similar properties, but he left gaps because he knew or he suspected that there was more elements out there that had not been discovered yet. Okay, there were certain spots in the periodic table that were left blank because he had the idea that there would be some elements that would fit in that spot. Okay, so nothing that was currently discovered fit there, but he assumed that elements would be discovered that would fit in those particular locations and follow the patterns he had laid out. Okay. He even went so far as to predict the new elements that would be discovered. Okay, he thought that there would be an element with a certain atomic mass that behaved like these that would fit in his table in a certain spot. Okay, so this was one smart cookie. Okay, he was right. He left these spots in his periodic table for elements to be discovered, and eventually they were. Okay, and they fit perfectly into where he had left a spot for them. Okay, so this guy knew what he was doing. Then this guy named Henry Moseley came along, and he decided that he needed to put the table in order of atomic number rather than atomic mass. Okay, and can someone tell me what atomic mass is? Yeah, Carolyn, what do you think? Perfect. Protons plus neutrons. So those two generally go together pretty well. Okay, the atomic number and the atomic mass are pretty proportionate, but not always. Okay, so he decided to list them in order of increasing atomic number. Okay, and atomic number, we said, was just the number of protons that an element has. Okay, Moseley's new system, going by atomic number, kind of helped these characteristics that Mendeleev had grouped them in, helped all these similar elements repeat at more regular intervals. Okay, so he helped the similar elements be grouped in a way that made sense kind of more regularly, I guess. And there's so many trends that are found in the periodic table now. It's kind of crazy to think that these guys did all of that so long ago. Okay, there's a lot of things that we can tell about an element just based on its spot in the periodic table. Order by increasing atomic number. Okay. It increases as you go from left to right and as you go from top to bottom. So the atomic number 1, which is hydrogen, starts in the top left. The largest atomic number is on the bottom right. Okay, so as you go across from left to right, it increases, and as you go down, it starts over, again from left to right. Okay, so just start getting a look at the periodic table in front of you so you can start becoming familiar with it. Okay, we start with element 1, which is hydrogen. Across is 2, which is helium. And then we move down a row. Lithium has an atomic number of 3, beryllium 4, and then we go across to boron, carbon, nitrogen, all those types of things. And we go down again. Okay, so I want you to start getting familiar with these elements, where they're found on the periodic table. Okay, and the atomic number on this particular periodic table is listed in the top middle of every box. Do we see that? Okay, and then what's the little number below? Atomic mass. That's its protons plus neutrons. Okay, so number at the top, atomic number. Number below is the atomic mass. Very good. Okay, this whole system of being arranged by atomic number is called periodic law. Okay, so when elements are arranged in an order of increasing atomic number, there's a periodic repetition of physical and chemical properties. That's what our periodic law states. Okay, when elements are arranged in order of increasing atomic number, not hashtag. Okay, no one laughed. All right, you guys don't even get. Okay, that's fine. No, yeah, we're not going to waste my jokes on you guys anymore. Okay, when we increase atomic number, we have a periodic repetition of properties, both chemical and physical. Okay? Okay, let's talk a little bit more extensively about the groups. What I want you to do on your periodic table that's in front of you, I want you to label the group numbers. And I'm going to give you a labeling system that I will use, and this is how I will speak, okay? See how many rows are right in this middle section? How many groups are in the middle section? Count them on your periodic table. How many groups are in the middle section, called the transition metals, which we'll get to in a second? 10. There's 10 groups. Okay? So if we go across the periodic table and label the groups, starting here, this would be group 1, group 2, okay? And then what we will do is jump over here and make this group 3, okay? This group can either be called group 3 or group 13, okay? Because there's 10 groups in the middle. But it's easier for us to deal with this being group 3, group 4, group 5, group 6, group 7, and group 8. And I'll explain that in a little bit as we start getting to talking about valence electrons. Labeling the group numbers this way helps us with valence electrons, okay? And that will come later. But this is just a way for us to get into that, okay? So starting with hydrogen, label them at the top here, just group 1, 2, then jump over 3, 4, 5, 6, 7, 8. Okay, so we are going to talk about 8 groups. So when I ask you about group 7, you should be looking at chlorine, bromine, iodine. Okay, does that make sense? All right, your book labels them the different way. Okay, your book calls this group 13, group 14, 15, 16, 17, 18. Okay? All right, does that make sense? Everyone's on the same page? Excellent. Okay, let's look at the periods now. These are rows, so they go from left to right. Okay, they lay flat. And if you're grouped in a row with other elements, you don't really have very similar properties. Okay, you share one characteristic, and that's the number of electron shells you have. But generally, as you move from left to right, you have changing properties. Although we see change as we move from left to right in a row or a period, things that are close together tend to act similarly. Okay, there's small changes between sodium and magnesium. Okay, small change between magnesium and aluminum, but big change between sodium and chlorine. Okay, those are in the same row, but they are very different. Okay, they have very different characteristics. So they might be similar to the one next to it or the one surrounding it, but they could be very different from something across the periodic table in the same row. Does that make sense? Okay. let's get to talking about metals. Okay, these are characteristics of metals that we're going to talk about, and these are ones that you'll need to know. Okay, you need to know what some characteristics of metals are. So they are shiny. They're good conductors of heat and electricity. Do we know what being a conductor means? It travels through them well. Okay, it can transfer heat and electricity very well. Okay. So I'm going to put these all up here, give you a second to write them down, and then we're going to talk through each of these points, and you can add some more notes if you want, okay? Let's talk through these characteristics of metals. Shiny kind of goes without saying, right? Most metals have a shine or a shimmer to them. Okay, that's obvious. Would that be an intensive or an extensive property? Intensive. Intensive means you don't matter. It doesn't matter how much of the object you have, right? Remember, intensive and extensive are a little different. Intensive means we don't matter. It doesn't matter how much of the substance we have. It's still going to be shiny, right? Is it a physical or a chemical property? It's a physical. So it's a physical intensive property. Okay? Very good. Conductors of heat and electricity, we talked about that. Those things travel well. Most are solid, which means they have a set volume and a set shape. Okay? They're malleable. Do we know what the term malleable means? Yeah, Trevor, what do you think?
You're sort of able to sculpt or mess with it.
Yeah. Okay. Typically, malleable means it can be pounded into sheets. Okay, you can pound it into very thin sheets. Okay, so what's a metal that we know of that's really malleable? Yeah, Carolyn. Aluminum. Good, right? Everybody has aluminum foil in their kitchen. It can be pounded into very thin sheets. Tin is the same way. We have lots of tin things that we've had put into sheets. I'm sure there's many, many others. Okay. To be ductile means it can be drawn into a thin wire. Okay, so it can be drawn and shaped into a thin wire. That's what ductile means. So what would be an example of a metal? Yeah, Braden?
Copper.
Copper wire. Very good. Okay, that's the most common example. Very good. Okay, and they have high tensile strength. Any idea what that means? Yeah, Andrew, what do you think?
How much tension they can hold.
Yeah, good. Typically, it's not going to break. It's not going to shatter. Okay, it has high tensile strength. You can pound on it, you can hit it, whatever. It's not going to shatter into a million pieces. Okay, it's very sturdy. Very good. Okay, we can have other characteristics that go along with metals, but for example, mercury is a liquid at most temperatures. Okay, that's a very, very interesting property of a metal. It's not normal. Okay. Some metals are so soft you can cut them with a butter knife. Sodium is an example of that. Okay, sodium is an extremely soft metal. Okay, so not very high tensile strength there. Very, very soft. Some of them have extremely high tensile strength. Chromium, tungsten, titanium, those are all very, very, very strong metals. Okay, iron. All right, most nonmetals are going to be gases at room temperature. Okay, gases at room temperature. Whereas metals were mostly solid at room temperature. Okay, most of these nonmetals are gases. Okay, so here's an example of some of our nonmetals. And are they found to the left or to the right of that stair-step line? The right. Okay, nonmetals are found to the right of that stair-step. Okay. Nonmetals, if they are found in solid form, are very brittle, which means they will shatter or break easily. Okay, here's some examples of those that may be solids. but are nonmetals? Okay, nonmetals do not conduct heat and electricity well at all. Okay, they are not good conductors of heat or electricity. We see most of these characteristics should be opposite of metal characteristics, right? Because those were metals, these are non-metals. They should be acting the opposite way. Okay? So here's just some pictures of nonmetals. You can't really take a picture of air, so that's what you get. Okay. All right, let's look at the metalloids, which are kind of the in-between guys. Okay, they have some characteristics of metals and some characteristics of nonmetals. Okay, they can do a little bit of both. These guys are most of the time solid at room temp. And they're kind of in between on their ability to be put into sheets or breaking or anything like that. So they're kind of malleable sometimes, but they're not as brittle as nonmetals. Okay, so you might be able to work with them a little bit. Okay, some of them have a metallic shine. Some of them like to shine like that. Antimony is a good example of that. Antimony has the symbol SB. Okay, so it fits right along that zigzag line, but it's labeled SB. Okay, so antimony is one of those in particular that is a little shiny, even though it's a metalloid. Okay, and finally, these guys are what we call semiconductors. So they're semi-good at it. Okay, so if you're looking at the board, the metalloids are the greens. The blues would be which group?
Non-metals.
The nonmetals. And then all the yellows would be metals. Good.